In electric power systems, frequency serves as an indicator of the balance between available energy generation and energy demanded consumption. It is closely linked to active power, such that an excess in active power results in an increase in frequency, and a deficit leads to a decrease. Frequency support pertains to the short-term balance of energy and frequency within the electric power system. It involves ancillary services that continuously modulate active power to maintain frequency within specified limits, thereby preventing potential load shedding, instability, and system loss. Frequency support is a crucial component of ancillary services in power systems. It ensures the stability and reliability of the electrical grid by maintaining the balance between supply and demand. Here are some key points about its importance. Grid stability. Frequency support helps maintain the grid frequency within a narrow range around its nominal value E.G, 50 Hz or 60 Hz. Deviations from this range can lead to instability and potential blackouts. Response to disturbances. When there is a sudden loss of generation or a spike in demand, frequency support services provide a rapid response to counteract these disturbances. This can involve either increasing generation or reducing load. Integration of renewable energy. With the increasing penetration of renewable energy sources like wind and solar, which are intermittent by nature, frequency support becomes even more critical. These sources do not provide the same inertial response as traditional fossil fuel generators, making frequency support essential for maintaining grid stability. Economic efficiency. By ensuring a stable frequency, ancillary services help avoid the costs associated with power outages and equipment damage. This contributes to the overall economic efficiency of the power system. Regulatory compliance. Many grid operators have specific requirements for frequency control that must be met to ensure the reliable operation of the power system. Ancillary services help in meeting these regulatory standards. Let us discuss about Fast Frequency Reserve. FFR, which is also known as Firm Frequency Reserve, is a rapid reserve mechanism that operates significantly faster than Frequency Containment Reserve. It is designed to address frequency issues quickly, providing enough time to activate the FCR. FFR is specifically defined for under-frequency situations, which are more critical than over-frequency scenarios. It can be achieved by rapidly injecting active power or reducing load in the system. There are two types of FFR, short support duration FFR lasting at least 5 seconds and long support duration FFR lasting at least 30 seconds. Both types must be activated within 1.3 seconds, either by a step change or a ramp. FFR can be provided through real inertia from rotating masses or emulated by power electronics interface sources, known as synthetic or virtual inertia. Potential providers of FFR include conventional generators, loads with under-frequency relays, HVDC interconnectors, doubly fed induction generators DFIG, full converter-based wind turbine generators, and energy storage systems. Frequency Containment Reserve is an active power operating reserve essential for continuously containing frequency deviations from the nominal value. FCR ensures the operational reliability of a synchronous area by stabilizing the system frequency within seconds to an acceptable steady-state value following a disturbance or incident. However, it does not restore the system frequency to its set point. FCR is automatically and locally activated. It typically responds instantly and must be maintained for up to 15 minutes before being released, with a full activation time of up to 30 seconds. FCR can be provided by energy storage systems, generators, or demand response. The term FCR is commonly used by many transmission system operators (TSOs). In the Union for the Coordination of Transmission of Electricity (UCTE), it is referred to as Primary Control Reserve, while the North American Electric Reliability Corporation (NERC) calls it Frequency Responsive Reserve. Take an example of Frequency Containment Reserve for normal operation FCRN, which is a specific ancillary service for the Nordic Electric Power System Finland, Norway, Sweden and Denmark with the purpose of balancing the system within the normal frequency band 49.90 smaller than 50.10 Hz. Since this is within the range of normal operation for the Nordic synchronous area, no sudden changes in production take place and the activation time is rather slow, normally regulated upwards-downwards within 2 to 3 minutes. Frequency Containment Reserve for Disturbances is another specific ancillary service for the Nordic electric power system with the purpose of stabilizing the system in case of disturbances where frequency drops below 49.9 Hz, and it will be completely committed at 49.5 Hz. 50% of the reserve is regulated upwards within 5 seconds and 100% of the reserve is regulated upwards within 30 seconds. Frequency Restoration Reserve is an active power operating reserve necessary to restore system frequency to the nominal value after sudden system imbalance occurrence E.G, the outage of a power plant. FRR aims to restore the system frequency in the timeframe defined within the given synchronous area by releasing system-wide frequency reserves. For large interconnected systems, where a decentralized frequency restoration control is implemented, FRR also aims to restore the balance between generation and load for each TSO, restoring power exchanges between TSOs to their set point. FRR is typically activated centrally and must have an activation time between 30 seconds up to 15 minutes depending on the specific requirements of the synchronous area. It can be provided by generators, demand response or energy storage systems. FRR replace FCR if the frequency deviation lasts longer than 30 seconds. Automatic Frequency Restoration Reserve AFRR is an automatic complement in the FRR process. The AFRR reserve differs from FCR in that the reserve is remotely controlled by a centralized controller while FCR is locally controlled. An advantage of AFRR over FCR is that it can be based on a merit order and can take congestions in the electric power system into account. Take an example of AFRR, which is the terminology used by ENTSOE. The term used by UCTE is Secondary Control Reserve. The term used by NERC is Spinning Reserve. Manual Frequency Restoration Reserve MFRR is used for power balancing and to handle congestions in normal and disturbance situations. MFRR is the main balancing resource which when manually activated replaces both remaining FCR and AFRR activations and brings frequency back to the frequency target. The required activation time is typically 15 minutes. MFRR is the terminology used by ENTSOE. The term used by UCTE is Tertiary Control Reserve. The term used by NERC is Spinning Reserve. Replacement Reserve RR for short is the active power reserve available to restore or support the required level of FRR to be prepared for additional system imbalances, including generation reserves. RR replaces utilized FRR, helps manage congestions in the electric power system, and brings the frequency and the interchanges back to their target values when FRRs are unable to perform these tasks. RR can be centrally activated manually or semi-automatically at the TSO or DSO control center in case of observed or expected sustained activation of FRR and in the absence of a market response. System operators can also use RR to anticipate unexpected system imbalances. RR has slower response times than other reserves but are capable of responding over longer durations. The activation time varies among TSOs and DSOs. The full activation time of the RR standard product is typically 30 minutes. The ramping period can be from 0 to 30 minutes. RRs are often high-cost generators that do not normally bid into bilateral or spot markets and can start within 30 minutes or loads that can be interrupted on 15 or 30 minutes notice. They are called upon infrequently but must be reserved through ongoing capacity payments to be available on short notice and at all times. RR is the ancillary service with the largest load participation, as the requirements specified by TSOs and DSOs for response time, communications and control are relatively load-friendly. The combination of a steady